Page 99 in your blue book. So hopefully by this time in your life, you know that there are two main types of energy. And those two main types of energy are kinetic energy and potential energy. Tell your partner what kinetic energy and potential energy refer to. Kinetic energy is the energy of motion, and potential energy is energy that is... Pardon me? Okay. Potential energy is energy that is stored. Okay. Whoops. I need to fix this because this is not very good paragraphing. Okay, so the law of conservation of energy, that's another thing you need to know. Energy cannot be created nor destroyed, only transformed from one type to another. So if you, the total energy in the universe is the kinetic energy plus the potential energy. The total energy remain the same, but the kinetic energy can become transformed into potential energy or vice versa. You can also have energy transferred from one place to another place. So the energy in one section can be lessened, but that's only by taking some of it and putting it somewhere else. The total energy of the universe stays the same. Does that make sense? Okay. All right. So kinetic energy, you're not really responsible for knowing all the different types, but it is kind of good to know. There is vibrational. Okay, and that is this one here, and I'm going to demonstrate for you. If I am a water molecule, or actually if I'm a CO2 molecule, CO2, let me get a little step stool here. One of the forms of vibration is bending. Okay, bending. The other form of vibration is symmetrical stretching. Yes? And the third form is asymmetrical stretching. So if a molecule is vibrating, it's either doing this, or it's doing this, or it's doing this. That's one type of motion. Another type of motion is rotational motion. So that's like spinning on its axis. So you can spin in one direction, you can spin, I cannot do cartwheels anymore. Too old, my shoulders hurt. Spinning in another direction, okay? And then translational is where you move actually like in a certain direction. And you can have all three of those going on at one time. Whew, that made me a little bit dizzy. Now, the faster a molecule moves in any of these ways, the more kinetic energy it has. The more a molecule does of any of these motions, the more kinetic energy it has. Do you know how you can make molecules move faster? Heat it up. You can heat it up. And what you'll be doing is you'll be transferring energy from, say, a hot plate to the energy, to the water in a beaker? Is good? Okay. Temperature. Temperature is literally a measure of the average kinetic energy. You should memorize that. It is an important piece of information that you should just know. So basically, if you have faster molecules, you have more kinetic energy. And if you have more kinetic energy, what's the temperature like? Temperature is higher. If you have slower molecules, you have less kinetic energy and your temperature is lower, okay? Potential energy that is, this is in the chemistry sense. There's lots of other senses. You know, you can have gravitational potential energy, but this is in the sense of chemistry. It is the energy stored in atoms and the bonds between atoms, okay? And do you remember how stability relates to potential energy? Things with high potential energy are less stable. Things with low potential energy are more stable. Okay. And in this particular section, because we're looking at a chemical reaction, we're looking at one substance being transformed into a different substance. We're also going to be looking at one form of energy being transformed into a different form of energy. So if we take kinetic energy and we turn it into some potential energy, what's going to happen to the speed of the molecules? It's going to be lower because we're going to have less kinetic energy, right? The molecules will move slower. If they're moving slower, the temperature is going to decrease. What is happening to the total amount of energy? Nothing, because you've just transformed some kinetic into potential. The two of them together still equal the same. If, on the other hand, we take potential energy and transform it into kinetic energy, now we have more kinetic energy. The molecules will move faster, the temperature will increase, and the total amount of energy will stay the same. Okay, good. So now say we have some reactants. And let's say that they have 2 kilojoules of potential energy. We also have some products, and the products have more potential energy. They have 12 kilojoules of potential energy. So we have our reactants with 2 kilojoules of potential energy, and our products with 12 kilojoules of potential energy. So energy stored in the reactants and energy stored in the products is different. How did the products get an extra 10 kilojoules of energy? Yes, we had to have 10 kilojoules of kinetic energy gets added into the system. And what happens to it as it goes through the reaction? Does it stay as kinetic energy? No, it is transformed into potential energy. Is good? Okay. We usually don't write the potential energy in our reactants because it is an integral part of the chemicals, but I will be writing it sort of underneath for now because it is good in thinking about how it works. Okay. So here's our example. We had reactants. They contain 2 kilojoules of potential energy. We have 10 kilojoules of kinetic energy. But we have 2 plus 10 kilojoules. The total energy before the reaction is 12 kilojoules. And the total energy of the after the reaction is 12 kilojoules. Where do you think this kinetic energy might have come from? Heat. That's going to be heat. So that would be like a hot plate or a flame, or even just the heat of like natural room temperature. Okay, it might suck some of the temperature out of the room. Yes? So this is coming from a hot plate, from a flame, or just from the ambient heat in the room. Do you guys know what ambient means? Sort of like natural. Just kind of like the surrounding heat in the room. Yes? How are you supposed to know what? Oh, you just need to know that that is kinetic energy. So that's energy of heat. So what's happening is that reaction is sucking in heat and it is turning it into kinetic energy. So where is that heat coming from? It could be coming from a hot plate. It could be coming from a flame. It could be coming just from the temperature of the room because we're not at absolute zero, right? So yeah, and that's not something I'm going to necessarily be asking you. We're just sort of setting the stage for where we're getting to, okay? So this is what that's going to look like on a graph. So on our y-axis, we have the potential energy, and that's in kilojoules. And on the x-axis, we have the direction of the reaction. So the reaction is proceeding forward. So we're starting with the reactants, and we're finishing with the products. And if you recall, the reactants contain 2 kilojoules of potential energy, and the products contain 12 kilojoules. Okay, so as we go from reactants to products, the potential energy must increase. Yes? Okay. Now, this little squiggly line with the kinetic energy, that's just showing that the kinetic energy is being absorbed and transformed into potential energy. So it is absorbed and transformed into potential energy. Eventually, you're going to be drawing graphs like this. You are not expected to draw the kinetic energy. It's just there so you can visualize what's happening right now, okay? what's going to happen if our kinetic energy is absorbed and transformed into potential energy? What will happen to our temperature? So kinetic energy is transformed into potential energy. In other words, kinetic energy is turning into potential energy. Yeah, since our kinetic energy is being used up, our temperature is going to be lower. Remember, temperature is a measure of average kinetic energy. So this is one place where people sometimes get confused because we say, in this reaction, heat is absorbed. So this kinetic energy, we often call it heat. Heat is absorbed and it gets colder. And people say, what? I just absorbed some heat. Should it not get hotter? But that usually misses the step that the heat is absorbed and then it is transformed into potential energy. So it's important that your brain make that distinction, that when heat is absorbed, it's not just absorbed, it's absorbed and then it's transformed into potential energy, so you have less heat than you did before. Does that make sense? So the temperature gets lower. This thing is big. Sorry about that. This thing is making all kinds of noise and I'd like to make it stop. There we go. So the temperature will decrease. This is called an endothermic reaction, since kinetic energy or heat has entered the system. Is this sounding familiar? Yes. Okay. Now let's say that you have some reactants in a chemical reaction, and these reactants have 9 kilojoules of potential energy. Your products have 1 kilojoule of potential energy. So in order for us to go from 9 kilojoules to 1 kilojoule, and that's a potential energy, what has to happen? How do we go from 9 kilojoules of potential energy to 1 kilojoule of potential energy? Yeah, some of those 9 kilojoules have to be transformed into kinetic energy. So 8 kilojoules. Oh, I've written it here. Why am I writing it again? Haha. So 8 kilojoules of potential energy have to be transformed into kinetic energy, and that kinetic energy, or the heat, is produced. Can you guess what kind of reaction this is? Exothermic. This is exothermic. Okay, so here to expound upon our example, we have our reactants that contain 9 kilojoules of potential energy. In our products, we have 1 kilojoule of potential energy and 8 kilojoules of kinetic energy. Together, that makes 9 kilojoules of energy in total. And this is 9 kilojoules of energy in total. All right. And on our graph, potential energy is on the y-axis. So that's our potential energy measured in kilojoules. And along the bottom goes the progress of the reaction, the direction of the reaction. So we start with reactants. We finish with products. The reactants have more potential energy. The products have less potential energy. And what happened to all that extra energy? Potential energy was transformed into kinetic energy, and it is released from the reaction. So do we have more kinetic energy than before or less? We have more kinetic energy than before. So what will happen to our temperature? It will increase. So this is an exothermic reaction. Kinetic energy, in other words, heat, has exited the system. All right. And if kinetic energy or heat has exited the system, it's going to feel hot. Can you think of an example of an exothermic reaction? Chat with your partner. Come up with something, where there's a chemical reaction and you know that it is exothermic. You guys honestly can't think of something that produces a nice warm fire? Any kind of combustion. Okay, so there's a reading check here. I will let you do that later. Okay, we are going to move on to 6.4b, which is on page 104. And we're just going to introduce, this is basically the same thing, but we're introducing a new word. And that new word is enthalpy. Enthalpy. Now, E stands for energy, so we can't use E to stand for enthalpy because that would be confusing. There's actually a lot of things that start with E, so we end up using the letter H, which is in the middle of the word. So enthalpy is represented by the letter H. Okay? Enthalpy, letter H. I guess it kind of seems like a little bit like heat, too. Yeah? Are you familiar with the Greek letter delta?
Yes.
Okay, what does it mean?
Change.
Change in. Okay, so it means change in. And when we are thinking about potential energy, we're usually thinking, was my potential energy increased? Did it go up? Or was my potential energy decreased? Did it go down? So we're actually looking at the change in potential energy, which for the purposes of Chemistry 11, enthalpy can be thought of as the chemical potential energy. That is an incorrect definition. I'll just let you know that right now. Okay? You don't even want to know what the correct definition is, but I will read it to you anyway. So you can be like, no, I like chemical potential energy. That sounds good to me. Let's see. Enthalpy. Glossary. Enthalpy, a quantity defined by the relationship H is equal to E plus PV. The enthalpy change, delta H, for a reaction that occurs at constant pressure is the heat evolved or absorbed in the reaction. Delta H is equal to QP. Do you like that definition, or shall we stick with the chemical potential energy? Chemical potential energy, yes. Okay, so if we are looking at the change in potential energy in a system, we're now going to call that the change in enthalpy. Okay, and we give that the symbol delta H, change in enthalpy. So in an endothermic reaction, we have kinetic energy transformed into potential energy. So therefore, the potential energy increases. And since we're essentially saying potential energy and enthalpy are the same, the enthalpy increases. And if something is increasing, that is a positive change, yes? So the change in enthalpy is positive. Delta H is positive for an endothermic reaction. So you can write delta H is equal to a positive value. Change in enthalpy is positive. Same thing, exothermic reaction. Potential energy is transformed into kinetic energy. So we're taking some potential energy and we're turning it into something else. So our potential energy decreases. That means our enthalpy decreases. And the change in enthalpy is negative. And now we're going to introduce you to the heat term. But we've already looked at it, so it's nothing new. We're just going to call it the heat term now. Here we have some gasoline burning. The enthalpy, the chemical potential energy, is converted into heat, and the heat is the kinetic energy. So here is our gasoline. Okay, that's gasoline. And what do we react it with? If it's combustion, C8H18 reacts with O2. And what are our products of combustion? CO2 and H2O. This would be a fun one to balance, wouldn't it? You end up with big numbers, 25 and so on. So if we have potential energy being converted into kinetic energy, remember potential energy is also known as enthalpy. What happens to the amount of enthalpy? Does it get higher or lower?
Lower.
It gets lower. So the reactants have higher enthalpy, the products have lower enthalpy. And what happened to that potential energy? It was transformed into kinetic energy, heat. And where does that heat go? Outward into the surroundings. Okay, so when you have the fire, it's not like that heat just stays in the fire, it comes out, and that's why if you stand 3 feet away from a fire, you feel the heat because you are in the surrounding area. Okay? So if we were to draw this, we start with you'll notice this is basically the same diagram we had before. What is on the x-axis, or sorry, on the y-axis? Potential energy in kilojoules, although we could now call it the enthalpy. Up to you. You can actually label it both ways. And the reactants have higher enthalpy, so they start up higher. Here's our reactants. Our products have a lower enthalpy. And if we draw an arrow from the start to the finish, that arrow points which direction? Down. If the arrow points down, is that an increase or a decrease? That is a decrease. And that means our change in enthalpy delta H is negative. So if delta H is negative, if we start with high potential energy and we finish with low potential energy, is this an endothermic or an exothermic reaction? This is exothermic. And if it is exothermic, what happens to the temperature? The temperature rises, increases. So there are two ways that you can write a reaction to show that it is exothermic. First thing we can do is we can take our heat term, the kilojoules, and we can put it on the right side of the chemical equation, and that's in the products. Okay, so our kilojoules go in the products. So the heat is being given off, it's being produced. You can write the word heat, or you can write the actual number of kilojoules. So that's one way that you can say, oh, I know I have an exothermic reaction because I have produced the heat. You'll notice, is this term coming into the arrow or out of the arrow? Here's my arrow. It's coming out of the arrow. In other words, it is exiting, which tells you that this reaction is exothermic. So these are ideas that you're going to be putting together. You're going to be saying, if my kilojoules are in the products, it's exothermic. If my graph starts high and finishes low, it is exothermic. If I am told that my change in enthalpy, my delta H, is negative, I know that it is exothermic. So you can tell that a reaction is exothermic if the delta H is negative, if the graph goes down, or if the heat term is in the products. Yes? Okay. So here's an equation. This is the second way to write an equation. Sometimes we don't put the kilojoules in the reaction. We write the delta H beside the reaction. All right, and when we write it beside the reaction, it's going to be negative. A negative delta H is exothermic. Take a look at are kilojoules when they're written in the reaction, and are kilojoules when they're written as a separate delta H. What do you notice that's different about those two numbers? One's negative, one's positive. Okay, it's because when things come out, the reaction is losing them. Yes, they're coming out of the reaction, so that's going to be negative. All right, so you just have to get that in your head. We never have like minus something in a reaction. If it's minus something, that means it's a product. Okay? So here's a little summary. Exothermic. In our graph, it's going to look like this. Delta H is negative. And when we have our reactants going to our products, our kilojoules will be in the products. That's exothermic. Could you guess about endothermic, what the difference would be? If we were to do endothermic, what would the graph look like? It'd be going up. The change in enthalpy would be positive. And when we write our chemical reaction, we would have reactants plus energy, or kilojoules, goes to products. So that's a little summary of each of them, okay? Here's another reaction. I'd like you to take a look at this one. Tell me, what type of reaction is this? Is this endothermic or exothermic? This is endothermic. What's the graph going to look like? It's going to go up or down? It's going to go up. Is kinetic energy transforming into potential energy, or is potential energy being transformed into kinetic energy? Kinetic to potential. Ooh, there's one more thing we should put over here in our little summary. Exothermic, the temperature does what? The temperature increases. And in endothermic, the temperature decreases. Okay. So here's the graph. Just as you predicted, the graph is going up. What's the delta H value? The delta H is positive or negative? Positive. You can see that the arrow goes up. Now, when you start labeling your change in enthalpy, I want you to be sure that your arrow touches the starting point and touches the end point. This is not delta H. That is a value smaller than delta H. So this is no. Okay, this is delta H. Yes. Does that make sense? Okay. Since delta H is positive, if you have a positive delta H, the reaction is endo or exo? Endo. And the temperature, therefore, is it increasing or decreasing? Decreasing. Do we write the heat term on the left side or the right side? Left side. Okay, we have a positive delta H. Okay, and then we have some exercises here. Now, we have about 25 minutes left. And I would actually like to do one more thing with you and then just mainly let you review for your quiz for homework. Yes? Okay. but I'm going to give you like homework from the enthalpy entropy for after your quiz. Does that make sense? Okay, so we've learned this today. So we're going to actually go to our next book. So this is your ivory colored book or your buff colored book, yellow, whatever you want to call it. Is there anyone who did not get a copy? It is just over here. Okay, so if you've not yet received a copy of Unit 7, it's in here and the answer key is right up there.
Miss Beth, can I use the water?
Yes, absolutely. Yes. When's the quiz? Tomorrow on reactions. Yes. And actually, let's just go over what's going to be on your quiz tomorrow. If I can make it go to a different team. Let's see. Teams. So wonderful. Okay, here we are. Chem 11. Upcoming quizzes and tests. So Tuesday, June 11th. That's tomorrow. You need to be able to recognize the type of the reaction, either from the entire reaction or from the reactants only. Yes? You need to be able to predict the products of synthesis, decomposition, single replacement, double replacement, combustion, and neutralization. You need to recognize if there is no reaction in a single replacement reaction, you will be given the activity table. Higher things can replace, lower things cannot replace higher things. You should also recognize if there is no reaction in a double replacement reaction, if both the products are soluble, aqueous, that means there's no reaction. You should be able to write the states of the products in a double replacement reaction. So if your product is soluble, aqueous. If it is low solubility, it is solid. You need to be able to balance reactions. And finally, I gave you a little extra practice on this today. You need to be able to write dissociation equations for salts, acids, and bases. You should also be able to recognize, is it a salt, an acid, or a base? You might choose to just do the odd letters, okay, or the odd numbers. Okay, there's a lot there, so you don't have to obviously do them all. And that is your quiz tomorrow. All right. We are not on solution stoichiometry yet. We are on, where is it? Mass and mole stoichiometry. And before we do that, I'm going to have you take your green sheet that you should have gotten, and we're just going to take a look at it. So this big weird word, and if you were away on Friday, it is pronounced stoichiometry. Okay, stoichiometry. And basically, it is converting moles of A to moles of B. And what we use is we use the mole ratio from the balanced equation. Essentially, we use the coefficients. All right. Now, you have a whole bunch of tools in your tool belt from Unit 5. Yes? If I were to give you grams of substance A, you could convert that into moles of substance A. What would you use? You would use the molar mass. And then you would use the ratio of coefficients from the balanced equation. If you have no idea what I'm talking about because you weren't here Friday, please watch the video from Friday's class and make sure you're caught up. If you're confused, come on in and see me at Flex or after school, okay? Once you know the moles of A, you can use the coefficients to convert to moles of B. But what if I didn't ask you for moles of B? What if I asked you for grams of B? You could use the molar mass to go to grams of B. So essentially in this unit, step number 1 is always going to be convert to moles. Step number 2 is always going to be convert from moles of A to moles of B. And then step number 3, maybe you're only asked for moles and you're done. Maybe you're asked to find the number of particles and you use 6.02 times 10 to the 23. Maybe you're asked to find the volume of a gas and you use 22.4 liters per mole. Maybe you're asked to find the volume of a solution and you use the molarity. Okay, so step number 1, convert to moles. Step number 2, moles of A to moles of B, and that's going to be using the coefficients. And then step number 3, use all those tools from your previous unit to convert. Now, should you want to use this sheet, again, that's going to be a 10% cost to you, but if you like to use it, that's fine, okay, on a quiz or a test. All right, so we can take all of these things, blah, 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 and we can say more simply, we can take whatever we know about A, we can convert it to moles of A, we can convert it to moles of B, and then we can figure out whatever we need to know. All right, that is stoichiometry. Yeah. Okay. There's also some other stuff here about limiting reactant and percent yield and all that kind of stuff. You don't need to know about that. Today, what we're going to look at is we are going to be looking at page 9. If you've not yet done page 8, that's going to be something you either will do tonight or tomorrow after your quiz. Hopefully you did it over the weekend, but you know, I don't know. I don't know what people do. So we're going to be looking at, in this unit, using molar mass, we're going to be using Avogadro's number, and we're going to be using molarity. Later on, we will also be using 22.4 liters per mole. And you can see, does this look kind of like that diagram on your green sheet? Okay, it's just been simplified a little bit. And today what we're going to be focusing on is we're just going to be focusing on mass. All right, so we're going to go from mass, use molar mass to convert to moles of A, to moles of B, to mass of B. So for example, we have the combustion of propane. What mass of CO2 is produced by reacting 2 moles of oxygen? So you can see that we are starting with moles of oxygen. Yeah, we're starting here, moles of oxygen. And we want to finish with the mass of a different substance, CO2. So how many steps are we going to do? We're going to use our moles to moles, and then our moles of B to grams of B. So we'll be starting with 2 moles of O2. We're going to convert that to moles of CO2, and then we're going to go from moles to grams. So let's try that. How many grams of CO2? And we're starting with 2.00 moles of O2. When you want to convert from moles of one thing to moles of a different thing, what do we use? Moles of A to moles of B. That's our mole ratio, okay? Moles of O2, moles of CO2, that is our mole ratio. Where do we get the numbers? From the coefficients. Okay, this is the only thing that's different is now we're using reactants. So we're not just getting it from the formula, we're getting it from the coefficients in the balanced reaction. So if we look at our, well, actually, before we do that, let's write down what we need to cancel. We need to cancel moles of O2. So that goes on the bottom. And we want to find moles of CO2. So that goes on the top. And then we're going to use our coefficients in here. So what is the coefficient for CO2? 3. That means for every 3 moles of CO2 that react or that are produced, how many moles of O2 did we need to use? We needed to use 5. Okay, I didn't give myself very much room here. So I'm now going to have to convert to grams of CO2, and I need to cancel moles of CO2. Carbon is 12, oxygen is 16 times 2 is 32, and 12 is 44. So that is 44, don't forget your 0.0 grams per 1 mole. We do our math on that. 2 times 3 divided by 5 times 44 is 52.8. And what's our unit? Grams of CO2. It's important when you're doing stoichiometry that you always write what substance you have because you're going to be switching between one substance and the other all the time. Okay? If you understood what was going on last day, this is just tacking on one extra step, okay? How are we feeling about that? Thumbs up, thumbs down, thumbs in the middle. We've got some thumbs up. Okay, good, 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 good. Would we like one more example? Okay, let's do one more example. This one, we want to know the mass of C3H8, so that's where we want to finish. Okay, that's our mass of C3H8. That's what we want to end up with. And we are starting with 100 grams of water. Okay, so we're starting here, so we're going to go through 1, 2, 3 steps. We start with 100 grams of water. Step number 1 is always convert to moles. And step number 2 is convert from moles of A to moles of B. And then step number 3, you figure out whatever you want. In this case, it's going to be mass. So let us start with, we want to find the grams of C3H8. And we're starting with 100.0 grams of H2O. You are not required to draw the map, but if you find you're not getting the correct answers, I would advise doing it. Do you know what I mean? Okay. What do we need to convert grams of H2O into? Moles. So let's cancel our grams of H2O and find moles of H2O. I happen to know the molar mass of water is 18. You might also know that or not. Doesn't matter. You can always add it up. So we have now gotten to our moles of H2O. Step number 2 is always go from moles of A to moles of B. So let's cancel our moles of H2O and find our moles of C3H8. When you have moles over moles, where do those numbers come from? The coefficients. Okay, so we go to our reaction. And where is our reaction? It's up here somewhere. C3H8, oh, there's no number, so that's a 1. And our water has a 4. So our water has a 4. And C3H8 had nothing, so it's just a 1. And finally, we're asked to go to grams of C3H3. So we need to cancel the moles of C3H3 and find grams of C3H3. 3 times 12 is 36 plus, or H8. Ooh, whoopsie. 3 times 12 is 36 plus 8 is 44. Is it another 44? 12 times 3 is 36. Oh, this should be H8. Do I have it? Have I written 3 all over the place here? So yeah, it should be 8. Oh, I need to fix this. I'm so sorry. This should be an 8 here, and this should be an 8 here. Fix. Okay. C3H8 doesn't work if you just have 3 of them. So anyway, that's another 44. 44, 1, and then you just do your math. 100 divide by 18, divide by 4, times 44 equals 61.1 grams of C3H8. Easy enough? Okay. So your homework for tonight is to study for your quiz. Now, how can you do that? In your book, in your blue book, what have I done with the blue book? The blue book's here. So pages 93 to 98 are good practice. Also good practice is the dissociation equations, the handout. And if you're like, I am all studied out for that, tomorrow's homework is going to be pages 102, 103. Page 107. And this is all in the blue book. And then your third thing is going to be in the ivory book. Pages 11 and 12. So if you're like, oh yes, I would like to get started on that because I understand how to do reactions and I'm not worried about it, go for it. But in the meantime, there you go. Yeah, for sure.
I need to a brain break. I told you.
Yeah, no problem.
Yeah.